To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today also I am going to discuss with you all electromagnetism and electromagnetic induction. So in the first chapter we looked at magnetism and magnets. So there you were able to understand that there are two types of magnets, the permanent magnet and the electromagnet. So permanent magnets have their magnetic field continuously. And there you were able to understand how the magnetic field exists around a bar magnet and a U magnet. That the magnetic field is a physical quantity with a magnitude and direction. And also you all saw how we can use a compass to observe the magnetic field. And before that we saw the materials that get attracted to magnets. So usually iron, steel and nickel are materials that get attracted to magnets. So we call them as magnetic materials. Whereas materials like plastic, wood, then rubber, these do not, or even glass, they do not get attracted to magnets. Even brass is not attracted to magnets. So that was what we observed about permanent magnets. Now in this chapter, we will try to understand electromagnets. So to understand about electromagnets, we will need to understand the magnetic effect of current. So here, magnetic effect of current. Now when we say magnetic effect of current, when an electric current flows through an electric conductor, a magnetic field is created in the vicinity of the conductor. So this is something you need to remember. So when there is a conductor, electric conductor, and a current is flowing through that conductor. So if there is a conductor like that and we connect it to a power source, and when there is current flowing through it, in this there can be a magnetic field generated. In the vicinity around the conductor, a magnetic field will be generated. So this is the conductor, and around the conductor there will be a magnetic field generated, and that is the magnetic effect of current. This particular magnetic effect of current was first discovered and observed by Hans Christian Ørsted. He is a Danish scientist. He is from Denmark. He is a Danish scientist. So there you can see a Danish scientist. Hans Christian Ørsted was the first to observe a magnetic effect in the vicinity of current carrying conductor. So he is the scientist who observed the magnetic effect of current for the first time. So that is when you supply current through a conductor, in the vicinity of the conductor there will be magnetic field generated. Now we will try to understand that as well. So with that I'll move on to the next slide. Here we will do an activity to understand the magnetic effect of current. So activity, observe a magnetic effect, that is a field due to a straight conductor carrying a current. And to do that activity, these are the apparatus that are required to us. So first we need a compass, insulated copper wire. Then we need the dry cells or batteries. Then we need the connecting wires. And also we need a switch. So what we will do is, we will use this insulated copper wire as our conductor. So that is what we will be using as the conductor, battery as the power source, and the connecting wires to connect the battery, the switch, and the insulated copper wire. And then we will use the compass to identify or observe whether there is a magnetic field generated around this copper wire or not. So that is how we are going to observe the magnetic effect or magnetic field due to a straight conductor carrying a current. So I will discuss the method in the next slide. So method. Now before we try to understand the method, I will explain it using the diagram given here. Now this is what we are going to do, students. Now we need to have this copper wire. It has to be a straight conductor. Now this copper wire can be used as a straight conductor, or what we can do is we can connect it to a circuit board. But if you do connect it to a board, a wooden board maybe, you have to make sure that you can place the compass below it. And we should be able to, anyway we can hold it above it, but we should be able to have the compass below it as well, without the compass touching the conductor. That is important. So what we do is we hold the conductor AB, we label it as AB, and then we place the compass below the copper conductor. And you observe whether there is a deflection there. Or else what you can do is you can place the compass on the table. You can allow the needle of the compass to align along the north-south direction. And on top of that, you can place the conductor AB. Is that clear? So AB also will be in the north-south direction. Thereafter, what we do is we connect the circuit like this. Now here you can see the AB conductor is there. The compass is below the conductor. Then we connect it using the connecting wires, the switch and the batteries. Now look at the batteries here. You can see the positive terminal is here. The negative terminal is there. When you close the switch, current will flow through the circuit. It will flow through this conductor. In which direction? Now this is the positive terminal, so current flows this way. Therefore, the current flow will be in the AB direction. At that instance, you need to observe the needle of the compass. You need to observe whether there is a deflection, and if there is a deflection, in what direction the deflection occurs. That is what you need to observe. Then what we do is we bring the compass above the wire. Or what we can do is we can off the switch and again observe the compass and see what happens to the needle of the compass. Then you bring the compass above the conducting wire AB or the conductor AB, and again you close the switch. You observe the needle of the compass. So in both instances, the current is flowing from A to B direction. But the first instance, the compass is below the conductor. The second instance, the compass is above the conductor. In both instances, you need to observe the pointer, the needle of the compass. After that, you again open the switch and then we change the terminals of the batteries. Now in this diagram, you can see this is the positive terminal, this is the negative terminal. Then also you connect the circuit. The conductor is in the same direction AB. Again the compass is below the conductor. Now again we close the switch and you observe the needle of the compass. Whether there is a deflection, and if there is deflection, in what direction. Then again you open the switch, observe the needle, and then you bring the compass above the conductor. Again close the switch and you observe the needle of the compass. So there are 5 instances. Initially, when there is no current flowing, you observe what happens. But these are the 4 instances where there is current flowing. In this one, current flows in the direction A to B, compass is below, compass is above the conductor. Then here current flows in the direction, now this is the positive charge, because of that current flows in the direction B to A. There again, compass below the conductor, compass above the conductor. So those are the 4 instances where you will have to observe. Is that clear, students? This is to understand the magnetic effect of current. So if we go and look at the method, place the compass on the table with its indicator along the north-south direction. So the indicator along the north-south direction, and next place the copper wire AB above the compass and along the north-south direction. So the copper wire is also in the north-south direction. Connect a battery and a switch to AB using connecting wires. Close the switch S and allow a current to pass through AB. Observe the indicator of the compass. Stop the current flow by opening switch S and observe the compass needle. Again, observe the indicator of the compass. Now change the terminals of the battery and allow a current to flow in the opposite direction BA. Place the compass below the wire AB. Observe the indicator of the compass. Now place the compass above the wire and allow the current to pass in the direction BA. Observe the indicator of the compass. So here, compass below the conductor, below the wire, and compass above the wire. So that is what I explained to you all. In this, the important things are we are changing the direction of the current flow and we are changing the position of the compass. So 2 changes. Direction of current flow, initially it's A to B, then B to A, and also position of the compass. Position of the compass. So one thing that we are observing is whether there is a deflection. Now if there is a deflection in the compass, from the previous activity you all know there will be a magnetic field. Normally if it is just the conductor there is no magnetic field. But when current is passing through it, if there is a magnetic field generated, there will be a deflection in the compass. And if there is a deflection, then you have to observe whether there is a relationship between the direction of the current flow and the direction of the deflection. And whether there is a relationship between the direction of the deflection and the position of the compass. So that is what you need to observe during this activity. Is that clear, students? So that you have understood the method, now let's go to the lab and do the activity. Okay, students. So now I am going to do this activity in order to observe the magnetic field that is generated due to the current flowing through a conductor. So to do this activity, I have 2 dry cells here connected together. You all can see the terminals positive, negative, and the terminals have been connected to the conducting wire. So you can see here this is a copper conducting wire, or this is the copper conductor. And that is in turn connected to the switch here. You can see the switch is now open. So here you all can see clearly, students, I have connected the 2 crocodile clips and you can see the terminals of the batteries. At the moment you can see, students, here it is the positive charge, here it is the negative charge. So you all know the current flows from positive terminal to the negative terminal through the external circuit. So it will start from here, go through the switch, then through the conductor from my right side to left side, and then back to the dry cells. That is how the current is going to flow. So here, students, we are going to change the direction of the current, and accordingly we will be looking at the deflection of the compass. So now if you look at the compass, you can see here it is at a balance. Now the pointer points this way from north to south. This side is the north and south. Now even if I place the compass under the conductor and allow it to settle, for the pointer to settle down, you can see there is no deflection. Why? Because there is no current flowing through the conductor. If you all compare this activity with the activity, the diagram given in your textbook, you all can remember the terminal, positive terminal is connected to the A end of the conductor. So we can consider this as the A end of the conductor and that as the B end of the conductor. So it is up to us students. The way we connect, we can label the conductor, ends of the conductor. Anyway, we will have to change the terminals of the battery. So if we first look at the compass here, now there is no current flowing because the switch is open. You can see the indicator, the point of the compass has settled down. There is no deflection. But if I close the switch, you have to observe the compass clearly. Now look at the pointer. You can see there is a deflection. If you consider the direction of the current flow this way, there is a deflection in the counterclockwise direction. The pointer moves this way. So it is a counterclockwise deflection. So that is one observation you have to remember. The pointer deflected in the anti-clockwise or counterclockwise direction. Now what I will do is, I will open the switch and then I will change the terminals of the battery. Now here, I have changed the terminals of the battery. This is the positive terminal, this is the negative terminal. So the current will now start from the positive terminal, flow this way. I said this is the end A, end B. From B to A, current will flow from B to A. We have changed the direction of the current now. Now look at the compass when I close the switch. So now you can see again the pointer is at equilibrium. Now when I close the switch, what happens to the pointer? It has moved this way. So that is the clockwise direction. So there is the deflection in the clockwise direction. Now can you all understand the difference? Now the current flow is this way from B to A, or you can look at the clips, black clip to red clip. There is a deflection in the clockwise direction. Earlier the current flow was from red to black. So there the deflection was in the anti-clockwise direction. So you can understand when we change the direction of the current, the deflection of the compass, the pointer changes. So that means the deflection is due to the magnetic field that has been generated. That is why there is a deflection. So the direction of the magnetic field depends on the direction of the current flow. To confirm this further, what we will do is, I'll open the switch again. While I keep the batteries this way, what I will do is, I will bring the compass above the conductor. Now earlier in both instances the compass was below the conductor. Now we will bring it above the conductor. Now you can see. Now can you see the deflection? It has rotated in the anti-clockwise direction. Above it is in the anti-clockwise direction. Below, if I place it below, you can see again it goes in the clockwise direction. So the direction of the current is the same. Direction of the current is the same from positive to negative terminal this way. When the compass is below, it is a clockwise rotation. But if I bring the compass above the conductor, you can see it is an anti-clockwise rotation. So there what happens? We say change the position of the compass. Why does the compass deflect? Because of the magnetic field. So the magnetic field above and below the conductor, the direction is different. The same way, I will again change the batteries, the terminals of the batteries. So here, again I have changed the terminals. This is the positive terminal, negative terminal. So now the current flow is going to be this way. Now observe the compass, no change. When I close the switch, again you can see it is an anti-clockwise rotation. But if I bring the compass above, now can you all see? It is a clockwise rotation. So below the conductor, it is an anti-clockwise rotation. Above the conductor, it is a clockwise rotation. So that is what you need to observe. So we have a conductor here. We pass electricity through that. Because of this current, there is a magnetic field generated. And this magnetic field depends on the direction of the current, whether it's from this side to this side or red to black. And also, the direction of the magnetic field is different below and above the conductor. That is what you need to understand from this activity. Okay, students. So, did you all observe the changes clearly? I'm sure you did. So, you were able to see that there was deflection in the needle of the compass when there was current flowing through the conductor AB. And what did you observe? When there was current flowing in the AB direction, when the compass was below the conductor, the deflection was towards the left-hand side. But when the compass was above the conductor, then the deflection was in the right-hand side direction, opposite. Thereafter, when we changed the terminals of the battery, what happened? Again, there was deflection in the compass, but opposite of the first instance. So, there the deflection was in the right-hand side direction. That is when the current was flowing in the BA direction. And there also, when the compass was below, the deflection was towards the right-hand side. But when the compass was above, the deflection was in the opposite direction. So, when we say deflects to the left, deflects to the right, what you need to understand is one thing, the direction of the deflection depends on the way the batteries were connected. When the current flows from AB, the deflection was of a particular direction. When you change the batteries and the current flows from B to A, the direction of the deflection changes. At the same time, when you have the batteries the same way, current is flowing from A to B, when you have the compass below the conductor, the deflection is in one direction. When you have the compass above the conductor, the deflection was opposite direction. That is what you need to understand. So, when a current flows through a conductor, there is magnetic field generated. That is one conclusion. And the direction of this magnetic field depends on the direction of the current flow. Whether it's from A to B or B to A, the direction changes. And at the same time, the direction of the magnetic field above the conductor and below the conductor are different. Those are the things you need to understand from this activity. I am sure you can understand that. So, if we write the observations. Now here, just to make it easy, I have given a few instances. The switch S is closed and a current is passing through AB. In that instance also, we looked at two observations. Compass is below and compass is above. So, here I will put below. Deflection of the indicator of the compass. When the compass was below, what was it? It was towards the left. Towards left. Then we had it above. Compass below and above. So there what happens? Again there was deflection in the indicator, but towards right. So here this again depends on how we label the A and B direction, students. If we label it the other way, then the directions would change, but still you will see when the compass is below, deflection will be towards one side. When you move the compass to the above the conductor, the deflection will be in the opposite direction. That is what is important. And also there is deflection only when there is current is passing through AB. Then the switch S is open and a current is not passing through AB. What happens there? There is no deflection. Then again, the switch S is closed and a current is passing through BA, opposite direction. Then also, the compass was below. You saw that the deflection was towards right. And the same instance, when we had the compass above it, towards left. So here, because you all know that there is deflection of the indicator of the compass, I have written the direction only. Here I have mentioned there is no deflection. Then again the switch S is open and a current is not passing through BA. Then also there is no deflection. So can you see that now? Earlier when current passes from, this is A to B, then B to A. That is important. So there, you can see when the current is flowing from A to B, when the compass is below, the deflection is towards the left. But when the current is passing from B to A, still the compass is below, the deflection is towards the right, opposite direction. So that means the deflection or the deflection depends on the direction of the current flow. Now this deflection indicates the magnetic field. So the direction of the magnetic field depends on the direction of the current flow. One thing. Then this is the first one you all were able to understand. When there is no current flow, no deflection. So that means only when the current is flowing through the conductor, there is magnetic field. And then, if you look at this instance, you can see the magnetic field above the conductor and below the conductor are different. That is why when the compass is below, the deflection is towards the left. When the compass is above, the deflection is towards the right. The same way here also it changes. Here when the compass is below, the deflection is towards the right. But when the compass is above, the deflection is towards left. It should be towards left. So that is how the deflection changes towards left. So from this, we can get a few conclusions. Deflection in the needle of the compass is seen when there is magnetic field in the vicinity of the conductor. That is there is magnetic field when a current flows through or we can say through the conductor. So that is one conclusion. Then you can see, then we can say the direction of the magnetic field depends on the direction of the current flow. Then the direction of the magnetic field is different below and above the conductor. So those are the conclusions that you were able to get. So I'm sure you understood the activity. This is how we got the observations. Like I said, students, if we label them differently, the direction of the deflection might change. But that is not something you'd have to worry about. Only thing is you need to understand that the direction of the deflection changes with the direction of the current flow and also depending on the position of the compass. And you need to understand there is deflection only when there is current flow. When there is no current flow, there is no deflection. Is that clear, students? So then, from all these observations, we got these conclusions. Deflection in the needle of the compass is seen when there is magnetic field in the vicinity of the conductor. That is, there is magnetic field when a current flows through the conductor. That is one. And the direction of the magnetic field depends on the direction of the current flow. The second conclusion. And finally, the direction of the magnetic field is different below and above the conductor. So all that you can understand. And those are the conclusions or the understanding that you get from the activity. So with that, students, I will move on to the next slide. The indicator deflects only when it is subjected to the influence of a magnetic field. So the indicator deflects only when it is subject to the effect of a magnetic field. That is in the presence of a magnetic field. This activity would show you that a magnetic field is created when a current flows through a conductor. A magnetic field is created when a current flows through a conductor. So that was the first conclusion I told you. Then, the second one, it will be clear to you from the above activity that the direction of the magnetic field in the vicinity of a current carrying conductor depends on the direction of the current flow. That was the second conclusion. And also you were able to see that the direction of the magnetic field above the conductor and below the conductor were different. Is that clear, students? So those were the observations or the understanding that we got from the activity. Is that clear? So with that, students, I am going to move on to the next slide where we try to understand the relationship of the direction of the current flow and the direction of the magnetic field. Direction of the magnetic field due to a current through a straight conductor. So to understand this, there are two methods or two rules that we can use. Here you can see, let us now investigate about two rules that could be used to find the direction of the magnetic field due to a current flowing through a straight conductor. And the first rule you can see here is known as the Maxwell corkscrew rule. You all know what a corkscrew is. It has a handle. Now you all know it has a handle like that and a screw like that, which you insert it into the cork of a bottle, and when you rotate it, the cork will be removed. You can rotate this corkscrew in two directions. You can rotate it towards the bottle and away from the bottle, and the direction of the rotation will change. So here, how we understand the direction of the magnetic field and the direction of the current is based on the direction of the movement of the corkscrew, whether it's into the bottle or away from the bottle, and the direction of the rotation. That is what is known as Maxwell's corkscrew rule. Maxwell's corkscrew rule can be used to find the direction of the magnetic field due to a current flowing through a conductor. So, Maxwell's corkscrew rule. Here, if we read the rule, this is something that is very important to you all students. When a corkscrew is rotated in such a way that its tip moves in the direction of the current flow, then the magnetic field lines produced by the current are in the direction of the rotation of the corkscrew. So, if you have the corkscrew here, if you are rotating it like that and the tip is moving downwards, direction of the current flow is downwards and the corkscrew is rotating this way. So, that will be the direction of the magnetic field. When we are moving it up, the direction of the current flow is upwards and the rotation is going to be in the opposite direction, whether it's a clockwise rotation or anti-clockwise rotation. So, that is how we find the relationship between the direction of the current and the direction of the magnetic field. So, you have to remember, students, when a corkscrew is rotated in such a way that its tip moves in the direction of the current flow, then the magnetic field lines produced by the current are in the direction of the rotation of the corkscrew. So, to understand this, we will go to the lab and do an activity where we observe the Maxwell's corkscrew rule using the previous activity. Now, the previous activity where I had the conductor AB, you can remember, we connected the dry cells, the batteries in two different directions so that the current flows from A to B and B to A. There also you were able to see that the magnetic field above and below the conductor were different. So, we are going to use that observation to understand the Maxwell corkscrew rule. So, let's go to the lab and observe the rule now. Okay, students, I am going to do this activity in order to observe the direction of the magnetic field when a current flows through a straight conductor. So, there are two ways in which you can identify the direction. One is known as the Maxwell corkscrew rule. The other one is known as the right hand grip rule. So, first I'll explain to you all the Maxwell corkscrew rule. So, you are familiar with the corkscrew, students. We use it to open the cork of a bottle. Similar to that, all the screws normally function the same way. They rotate the same way. So, in Similar to that, I have a G-clamp here with a screw there. So this is the screw that we are going to use in order to observe the direction of the magnetic field. So what you need to do is you have to consider this tip, the direction of the movement of the tip. Say if it moves from here to here, that is the direction of the current flow. Now if the tip moves from here to backwards, that will be the direction of the current flow. So you have to always look at the tip. So what we will do is we will rotate the screw so that it moves in one direction. Now if you look at it carefully, when I rotate it this way, in the clockwise direction, what is happening to the screw? Now you saw the screw was here, it has come up to this point. Again look closely. So the screw came from here to here. That is the direction of the tip of the screw movement. So that is the direction of the current flow. So if this was a conductor, current flows from here to here, from this end to this end, then the magnetic field is in the direction of the rotation. I will bring it back and explain it to you all again. Now here the movement of the tip is the direction of the current flow. So it's going to go from here to here, from my right to the left side. So at the same time, I'm going to rotate the screw in the clockwise direction. So that is the direction of the current flow. Can you all understand that? So that is the Maxwell corkscrew rule. We will try to understand this with the direction of magnetic field when the current flows through a conductor. Now here students, you can see like how I have connected the batteries. This is the circuit I used for the previous activity also to observe the magnetic field around a conductor through which current flows. So in this you can see this is the positive terminal. So when the switch is closed, current will flow this way from this red clip towards the black clip. Just look at the colors, it's easy for you all to understand, from the red clip to the black clip. So same as this clamp, like I did from here to here. So from this side to this side is the direction of the current flow. So at that time you can remember I rotated the screw this way, clockwise direction. Let's observe how the pointer of the compass deflects when I close the switch. So observe the pointer of the compass when I close the switch. Now when I close the switch, you can see the pointer deflects this way. That means the magnetic field is from there to here. It is in this direction. It is a clockwise rotation. So here you can see if we rotate it clockwise, the circle is going to be from this side to that side and below from there to here. So that is why the pointer moves this way. Can you all understand that? Now the current is flowing this way, magnetic field is around that. So when we have the compass below, the magnetic field is going to be in this direction. Like I rotate this way. So it's going to move like this. So the pointer points to this direction. It deflects in the anti-clockwise direction. That is how the effect of magnetic field or direction of magnetic field is around a conductor. Now, if we change the direction of the current flow, for that I will change the clamp and also I'll open the switch and I'll change the batteries. Now here you can see this is the positive terminal. So current flows here and in the conductor current will flow from black color to red color end. From this end to this end. Then if you can remember, first we will look at the compass. If I close the switch, you can see the pointer deflects in the clockwise direction. So there. Here we have the corkscrew. This is the tip of the corkscrew. So that's going to move in this direction. And at that time, now how do we rotate this? The tip has to move from here to here, this side to this side. So I will have to rotate it this way in an clockwise direction this way. But at the point, you have to see how this part moves below the conductor. Below the conductor, it goes like that. From here to there. From here to there. So the point also moved that way. Can you all understand that? So that is how the magnetic field will be. If we rotate it this way. Rotating it in this direction. So below the conductor, the deflection is towards that side. That is how we identify the magnetic field. So here, of course, it is going to be this direction. It's going to be a clockwise direction like this. So that is how we identify the direction of the magnetic field using the Maxwell corkscrew rule. Okay, students. So did you all observe the Maxwell corkscrew rule clearly? I'm sure you did. So now again, I will read the explanation, and with that, I will explain the activity to you all. So here you can see, a corkscrew is an instrument used to open bottles with cork lids. That is something I told you all. Normal screws show the same behavior as corkscrews. So when we say normal screws, the screw nails that are used to move, the nails that are used to fix things, the screw nails where there is rotation, they function in the same manner as a corkscrew. So there you can see there is figure A and B given to you all, and also figure C. A and B show you the direction of the current flow and the magnetic field. So you can remember, when we move the corkscrew this way, if it is the anti-clockwise direction, when you move it that way, here you can see. Now when the corkscrew is moving in the anti-clockwise direction, the current flow is from A to B. So there you can see the magnetic field lines are in the direction of the rotation. They are going to rotate in the anti-clockwise direction. So if you look at the lines there, below the conductor, it is this way. From here to here, you can see the arrowhead there. And above the conductor, the arrowhead points that way. So that is how you have the magnetic field lines. Now can you all remember the deflection? I showed it to you all when I went to the lab now. You were able to see the deflection of the compass when we had the compass below the conductor, and when the direction of the current flow was from A to B like that. The compass deflects this way, left side. So can you see the arrowhead there? That is the direction of the magnetic field. But when I brought the compass above, what did you all see? The deflection was towards the right side. Now can you see the lines here? So that is the Maxwell corkscrew rule. When the current is flowing from A to B, the rotation is in the anti-clockwise direction. So that is the magnetic field. Then look at diagram B. When you are rotating the corkscrew this way and the corkscrew is moving down, the current is flowing from B to A, downward current. Then you can see the magnetic field lines are like that. Now below the conductor, current is that way. So the deflection of the compass is towards the right hand side. But above the conductor, the magnetic fields are in this direction. So the deflection of the compass is going to be towards the left side. But if you look at the conductor, there is magnetic field around the conductor. So that is how we use the Maxwell corkscrew rule. You rotate the corkscrew. Now like this, when you rotate, it is going to move downwards. And the rotation is going to be this way, clockwise. Now going to rotate it this way. So the clockwise direction is the magnetic field lines. And the direction of the current flow is from B to A. If the direction of the current flow is from A to B, the current is flowing upwards, the magnetic fields are going to be in the anti-clockwise direction, this way. So that is how we use the Maxwell corkscrew rule. Now here, look at these two diagrams also. This is the conductor. So like the conductor AB that you all saw, the direction of the current flow is shown by this red color arrow, and you can see the direction of the magnetic field shown by this red color curved arrows. So direction of motion of the corkscrew gives the direction of the current flow. So here you can see this is the corkscrew. So it's going to move this way. Now we are going to rotate it like that. So the corkscrew will move this way and the rotation is also like that. So then that is the direction of the magnetic field. This is the direction of the current flow. If the corkscrew rotates the other way, if it's going in the opposite direction, direction of the current flow will be that side and the magnetic field lines are going to be outwards. So that's how the Maxwell corkscrew rule works. I'm sure with the activity you all got a good understanding. So here, A. According to figure A, when a current flows from A to B, the direction of the resulting magnetic field is anti-clockwise. So here you can see, according to figure A, when a current flows from A to B, the direction of the resulting magnetic field is anti-clockwise. And according to figure B, when a current flows from B to A, the direction of the resulting magnetic field is clockwise. So this is the figure that is showing you all the effect. But before I came here, I showed this in the lab. So I'm sure you all can understand how we can use the Maxwell corkscrew rule to observe the direction of the magnetic field. So just to look at the Maxwell corkscrew rule, this is the one. When a corkscrew is rotated in such a way that its tip moves in the direction of the current flow, then the magnetic field lines produced by the current are in the direction of rotation of the corkscrew. Is that clear? So that is one method of understanding the direction of the magnetic field when a current is passing through a conductor. Then there is a second method. We will look at that now. That method is known as the right hand grip rule. So when we say right hand, you all know this is my right hand. Now here I have a conductor. What I do is I place my thumb in the direction of the current flow. Say this is the conductor AB. Now if I place my thumb this way, that means the current is flowing upwards, AB direction. And then I fold the other four fingers around it. And that is the direction of the magnetic field. Here you can see anti-clockwise direction. This is the same as the previous rule. The way you identify the magnetic field lines is different. So I'm going to go back. Now here you can see. Like I showed you all, now the current is flowing upwards. So my thumb is facing upwards and my other fingers are like that. So it is the anti-clockwise direction. Now this is known as the right hand grip rule. Now for this instance, diagram B, what is happening? The current flows downwards. So my thumb, I have to always use my right hand. Thumb has to be downwards. So it's going to be like that. Now look at my other fingers. They are in this clockwise manner. So when the current is flowing down, thumb points downwards, my other fingers point to the direction of the magnetic field lines. So that is how we use the right hand grip rule. This is the Maxwell corkscrew rule. This is the right hand grip rule, but both of them give the same result. So that is what I am going to discuss here. Right hand grip rule. Right hand grip rule is another simple rule for finding the direction of the magnetic field due to a current carrying conductor. So here that is due to a current carrying conductor. If the conductor is held with the right hand in such a way that the thumb is directed towards the direction of the current flow. Thumb is directed towards the direction of the current flow. You have to use the right hand. Then the direction of the other four fingers around the conductor indicates the direction of the magnetic field. If the conductor is held with the right hand in such a way that the thumb is directed towards the direction of the current flow, then the direction of the other four fingers around the conductor indicates the direction of the magnetic field. So that is what I demonstrated now. But to understand this more clearly, like I did before with the previous activity where we had the copper wire conductor AB, we use the compass. With that same activity, I will explain this right hand grip rule as well. So let's go to the lab and do the activity now. Okay, students. So now I am going to do this activity in order to observe how we can use the right hand grip rule in order to identify the direction of the magnetic field due to a current flowing through a straight conductor. So in the previous activity, we observed the corkscrew rule. So here I am going to use the right hand grip rule. So to explain that, I am going to use this pencil here. Now if you look at the pencil, look at the tip of the pencil. Now this tip is the direction of the current flow. So what we need to do is we need to use our right hand and we have to place the thumb in the direction of the current flow. So here the current is flowing this way towards the tip. I have to place the thumb towards the tip of the pencil and I have to fold my other fingers like this. So now the direction of the fingers is the direction of the magnetic field. Current is flowing this way. This is the direction of the magnetic field. That is how we use the right hand grip rule. So let's say if the current is flowing in the opposite direction. Now the current is going from here to here towards the tip of the pencil. So again you have to place the thumb towards the tip of the pencil and you have to fold your fingers. Now can you see? The direction of the magnetic field is opposite. Now it is like a clockwise direction when the current flows this way. If the current flows that way, the direction changes. Now it becomes this way, the direction of these fingers. That is how we identify the direction of the magnetic field. Now we will look at this using the conductor as well. The same setup I used for the previous activities. So as you can see, I have connected the terminals of the battery. You can see positive terminal, negative terminal. So from the positive terminal through the external circuit, current will flow this way. So in this conductor, the current is going to flow from the red color clip towards the black color clip. So if you are to place the pencil, how do we place it? This way. Why? This is the direction of the current flow, so it's going to be this way. So if we hold the thumb like that, it has to go this way. So if it is this conductor, the magnetic field has to be in this direction. Current is flowing that way. Magnetic field below the conductor will be from this side to this side, like my fingers. It's going to be like that. Let's compare it with the observation. So if I close the switch, now can you see? The pointer deflects in this direction. So the fingers are towards this direction. So that is how we compare. Look at my fingers and the deflection of the pointer. They are in the same direction. So that is the direction of the magnetic field below the conductor. So if this is going to be the conductor, you have to hold it, grip it this way. So around the conductor, this is how the magnetic field will work. Is that clear, student? So then what will happen if we change the terminals of the battery? Let's see. I'll open the switch. I'll change the terminals of the battery. Now here you can see this is the positive terminal, this is the negative terminal. So current will flow in this direction. We need to place the pencil. Like I said, the tip is the direction of the current. Always you have to use the right hand. So if it is going to be like that, you place the thumb towards the direction of the current, fold your fingers, direction of the fingers, how the fingers point is the direction of the magnetic field. So it's going to be like this. So if this is the conductor, the magnetic field will be that way. So below since the compass is below, fingers are going from this side to this side. It's towards you. So above the conductor, it's going to come towards me. That's how the grip rule works. It's going to be like that. So let's observe it with the current flow. When I close the switch, now can you all see? The deflector points, rotates towards that way, clockwise rotation. So if it is the grip rule, fingers go that way and above they come towards me. So that is why the pointer deflects in that direction. Is that clear to you? So this is how we use the right hand grip rule. Always use your right hand. Thumb should point towards the direction of the current, and when you fold your fingers, they show the direction of the magnetic field. So children, you all were able to see this right hand grip rule. I demonstrated it using the activity. So you were able to see. Now if this is the conductor, that is the pen, you have to hold it with the right hand. The direction of the thumb, here you can see direction of the thumb points to the direction of the current flow. Then the other four fingers, here you can see the other four fingers points to the direction of the magnetic field. So if the current flow is this way, magnetic field is going to be like that. So conductor, magnetic field, electric current, and it is the right hand, and finding the direction of magnetic field from the direction of current flow. So if it is flowing in the opposite direction, if my thumb is pointing towards me, then you can see the other fingers are going like that, opposite of this. So there the magnetic field lines are in the opposite direction. I'm sure you all understood this more clearly with the activity. So always you need to use your right hand. Thumb should point towards the direction of the current flow. The other four fingers point to the direction of the magnetic field. So this also gives the same result as the Maxwell corkscrew rule. I'm sure you all can understand that. So with that, students, we will move on to the next slide. So here we have a figure where we need to identify or denote the direction of the magnetic field. Now, all this time I was saying, no, when we hold the grip, the conductor this way, the magnetic field lines are in a circular manner. You get circular magnetic field lines. So we can either say clockwise direction or anti-clockwise direction. But if we want to show it or mark it in a diagram, if we want to show it on a piece of paper, then we need to have symbols. So that is what we will try to understand here. Figure shows how the direction of the magnetic field due to a current carrying conductor is marked in a diagram. So to do that, we use two symbols. One symbol is this. We have a dot like that. Around that, we have a circle. The other one, we have a cross and there is a circle. Now this dot and a circle means the lines are coming out of the paper. This is out of the paper. So it is out of the paper, or we can say page. Then this cross and a circle around it means into the paper. Into the paper or page. So now we have a conductor AB. You can see electric current is denoted in the direction with the red color arrows. So here, direction of the magnetic field is into the page, direction of the magnetic field is out of the page. So if you use the Maxwell corkscrew rule or the right hand grip rule, you all know it's going to be like that. Current flow this way. Now here you can see from top, the magnetic field lines are coming out. We need to show that. What we do is, we put a dot and a circle around it. A dot and a circle around it. So that shows the magnetic field lines are coming out. But when we hold it this way, now below the conductor, the field lines are going into the page. To show that, what we do is, we put a circle with a cross. So this shows that the field lines are coming out of the page. This shows the field lines are going into the page. So that is the same as having this right hand grip rule or using the Maxwell corkscrew rule. Tip of the corkscrew will move that way and the rotation is going to be like this. So above, the field lines are coming out and below the field lines are going in. Now here you can see indicating the magnetic fields perpendicular to the plane of the page, directed into and directed out of the page in a diagram. So this is to diagrammatically represent the magnetic field. Is that clear? So far students, you all were able to understand that when a current is flowing through a conductor, there is magnetic field generated. That is what we call as electromagnetism. So this electromagnetic field that is induced has a direction, because the magnetic field has a magnitude and a direction. That is what we try to understand here. So you were able to see how the magnetic field is. That is when we use the compass. And then you understood the two rules, the Maxwell corkscrew rule and the right hand grip rule. Using that, you can identify the direction of the magnetic field lines based on the direction of the current flow. Then now we have understood how we can denote it in a diagram. If the conductor is this way and the current is flowing that way, how you denote the magnetic field lines. Now let's say, if we have another instance where the conductor is like this and the current flow is going to be in this direction. The current is flowing in that direction, different from the previous one. Now earlier the current flow was in that direction. Now the current flow is in this direction. So if we use the right hand grip rule, what do you think? The thumb has to point this way and the field lines above it's going into the paper, below it's coming out of the paper. So how do we denote that? You need to have a circle and here we need to have a cross because the lines are going in. Here the lines are going in and here the lines are coming out. So you will have the magnetic field lines this way, like that, going there and coming out. So that is how we denote the direction of the magnetic field line. So here the red color arrows point to the direction of the current flow, and then we have the magnetic field lines going into the page and magnetic field lines coming out of the page. So that is how we denote the direction of the magnetic field line. Is that clear? So with that, students, I will move on to the next slide. So here we can see, suppose that a current flows through the conductor in figure along the direction AB, then according to the right hand rule, the magnetic field is directed towards you, that is from the page in the region above the conductor, while it is directed away from you into the page in the region below the conductor. So this is what we already discussed. In the previous one, I explained this to you all. Now when the current is flowing through the conductor this way, you can see when we use the right hand grip rule, the magnetic field is, here you can see, magnetic field is directed towards you in the region above the conductor, and it is directed away from you, that is into the page in the region below the conductor. And then a dot inside a circle is used to indicate a magnetic field coming out of the page, while a cross inside a circle is used to indicate the magnetic field going into the page. So based on that, like I showed you all in the diagram, we use a circle like that, and here we have a dot because the direction of the magnetic field is out of the page, and here we have a cross because the direction of the magnetic field is into the page. So same thing what I explained before. Is that clear, students? So you should know to identify the direction of the magnetic field based on the direction of the current, and you should know to denote that in a diagram. So with that, students, I am going to end this chapter, and in the next chapter also we will continue the discussion where when there is magnetic field and current flowing through it, whether there is a force generated, and if so, how this force acts on the conductor. So that will be our next chapter.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.